So we were discussing on stuff, array-based representations, and then if we're gonna do that array-based representation using Q, then we usually run into a problem of what? We like to avoid cases that shifting elements inside the array. We know that that's a time-consuming task. We like to come up with a way of not to do that, right? Crystal, did we discuss that on Monday? Or did we discuss something completely different? Not listening to me today. You guys will listen to me when I start talking about the midterm right away. Anyway, so that's why we wanted to take a look at the approaches for circular array way of implementing queues, right? That was the way of it is. I mean, if you still don't remember, I was drawing on the board like these ones. Front, rear, and these things moving around. Front usually going into counterclockwise. No, this way. We're moving this way. But when we start, front should be the counterclockwise one next to the first elements. Rear is pointing to the last element in the list. And then the basic idea is we're moving these things around instead of moving the elements itself, right? What was the problem of doing this? What was the two cases that we should be careful of? Correct. Thank you. When they are pointing to a same location, unless we introduce some type of checking variables, we don't know whether they are full or empty. Those are the two cases that we should be careful of. What was the solution to those, distinguishing those two cases? Yeah, flag. What kind of flag was it? I mean, there was one flag. There's another one. I think was a counter, more of. Like add the flag, like checking whether your last operation is a add an element. If it wasn't add an elements, then, and at the same time, the pointer front and rear is pointing to a same location, then if it was an add, then I might say it's a full queue, right? Otherwise, it's not the full queue. Or we could use a counter variables that every time you do an addition +1, every time you do a deletion -1, then you check the value whether that's a 0 or greater than 0 or not. And then you can find out whether it indicates full queue or a empty queues, right? Those are the two conditions that you can find out. Of course, we're still talking about the array-based representation for these queues, right? You guys are busy studying with the other courses. When is the exam? 언제야 시험? Okay. I understand. Okay, and then 시간도 몰라. 자기네들끼리 시간으로 싸우고 있어. And then we were discussing on the using chains, using linked list. I mean, that was a typical way of doing it in other data structures, right? So queue will be the same as other structures. But comparing to a stack example of linked list, we don't have too much dispute on which end should be the front or rear. I mean, it doesn't really matter which end will be because the time complexity still requires on either end. So we saw that it's not going to be much of an impact. Unlike the stack examples, for stack, if we keep the left end as a bottom, left end as a top, then the top. Left hand as a bottom, then you should go into, in order to In case of stack, if you treat right end as a stack, right end as a top of the stack, then you have to go through n times in order to add and delete the elements. So we wanted to avoid such cases that we most likely wanted to have a top part on the left side where it begins, right? In Q cases, it doesn't really matter because we have to travel one way or the other. So that was the case we were discussing. This was a picture of a using chain or linked list. Doesn't matter which one you call it. So that was the basic ADT's definitions, and they briefly give you the ideas of how to implement each. I'm sure on the textbook they give you a bit more details on the coding itself. Please do take a look at it, and keep in mind that time complexity of each, if they don't say in the textbook, you can by now you can figure on yourself too. I mean, those are easy ones. Mostly constant operations too, right? Okay. That was about the Q part. Did I miss anything? No, I hope not. So this was a problem that I mentioning last class. Parenthesis matching problem. May not be able to do it with the Q part, only stack. Stack is much more convenient. Towers of Hanoi as well. Switching box routing. This will come up in next few slides. Method invocation and return. I also said it's more of a, you calling a function within your program, they need a memory space for the functions, but sometimes, most of the cases, we don't know which function will be called. So stack is the way of extending the memory part for that. So don't worry about it too much for us. It's more of other courses. But the thing is, it cannot be also replaced with the Q. But there are problems that can be replaced with the Q that is originally using stack. The first one, the obvious one is railroad car or rearrangement problems. I asked 3 times to read this from the book, right? The figures on, I think it's section 8.53. In those sections, they discuss the way of solving this car rearrange problem in stack. In chapter 9, 9.51, they're mentioning for the same problem using Q. What was the railroad car problems, whatever? I'm just gonna call it as railroad problems. It's just too long. What was the problem again? Just in case people who didn't look at it yet. 아직 안 봤겠지. Just because this is not covered in midterm, no one is willing to look at it yet. So if you look at this page, then they draw this way. Again, my wonderful artistic ability will get you the idea of a trains. Train. Yeah, I don't even do this to my son either. 애기한테도 해도 안 볼 거야 아마. Anyway, imagine things like this, and each car has their own numbers, and this is input line, so this is railroad. So they wanted to, when they out of this track, they wanted to be sorted out. The example they give on the book, it goes like 3, 6. Sorry, I can't remember. 3, 6, 9, 2, 4. 누가 좀 불러줘. 3, 6, 9, 2, 4. 아니다. 2, 4. 2, 4, 7, 1, 8, 5. So this is the order they have, but they give you 3 tracks. They go like this. It doesn't matter which one is number 1 or 2. So this is the track that you can spare. So you can make a decision on which number of cards should be in where, and this one is like a queue. Same example, similar problem. When we're using a stack, they draw it this way. If you take a look at 8.3, they go. Do you remember? And they probably call it as H1, H2, H3. And train is coming this way. And they take one out, put it in the bottom. So fill it in from the bottom, like that. That's also possible, but let's take a look at this queue approach. So it's nicely, very nicely explained in the textbook too, so you can read it. But let me just do it first few steps. So 3 is the first one. But bottom line is I like to be this 1, 2, 3, 4, 5, 6 in order. I don't know, for some reason that's more convenient later on. Okay, so my first cart is 3. I look at this tracks. Wow, 3 is everyone. 3, but it's not a 1. If it's a 1, I could just pass it through, but it's not 1. So I'm gonna put 3 in just empty ones. 3. Okay. Next one is 6. I'm just gonna do the textbook way of doing it. 6. But we know that 6 can come after 3. So we're looking at this. Oh, I can put still on the same queue and a 6. That's good. That's good. Okay. Because 6 is coming after 3. Next one is 9. 9. Looking at the queue, 2 is empty. 9 is coming next to 6. So that's okay. So I'm going to put 9 in here. 2. Next one is 2. Okay. Look at my queue. Look at my queue. Obviously, I cannot put 2 after 9 because 2 should come before 9, right? So I have an empty queue right here. So I'm just going to put the queue in H2. Okay. Good. I'm using my queues, right? These tracks are queues. Next one, 4. Same way, 9, 4, no. 9, 4 should be before 9. 9, 2, that makes sense, right? 2. 4 should come after 2. So 7, I guess 7 should be here as well. Okay, I'm in here. Now I have a 1. This should be the first. I go through 1, up, 1, out. 8. 뭐지? 8 should be, if I have enough space, 8, 5. Maybe I can put it in here. I mean, textbook way is slightly different. 5. Okay, I'm using my cues. Next thing, what am I doing? Just looking at this cue, putting it out. 2, 3, 4, 5, 6, 7, 8, 9. Are we good? Okay. Yeah. There are some cases that you cannot do with this. In those cases, then you need more cue. 그 책에서도 딱 써 있어요. 속된 말로 거지같이 꼬여 있는 경우는 풀 수 없는 경우도 있습니다. 네, 있습니다. 그렇게 익스트림한 케이스도 있습니다. 그럴 경우에는 이렇게 생각하면 훨씬 편한데. 그러면 어떻게 하면 제일 좋아? 그러니까 단순하게 생각하면 Q가 이게 9개면 Q가 9개 있으면 문제 없죠. 그죠? 그렇게 생각해도 돼요. So actually the running time of this algorithm will be based on the maybe how many queues I have, how many cards that I have. 그죠? 돈만 있으면요, 뭐 9개 쭉 갖다 놔면 되는데. 네, 맞습니다. 좋은 질문이고요. 책에도 비슷한 게 나처럼 이렇게 익스트림한 케이스를 설명해 놓지는 않았더라도 비슷한 요지로 설명을 해놨을 겁니다. So this is a Q way of doing it, and his question was on that part. What if it's one is at the back? There are some cases that you might need more Qs than just 2 or 3. Okay. So the performance of this implementation, if you want to implement this, then it will be strictly on those how many tracks, how many cars that you have. So that's a good question. Okay, so this is a QA. Originally, we look at this in stack way, but if you look at the stack example, they try to give you some extra conditions. They have to check how much is difference between the coming one and among the card numbers that is already in the stack. So if you read that, you might feel that there are some extra conditions I need to check. This one is less condition, less complicated. Anyway, bottom line is I can do same problem using two different structures. This is nice. You have a luxury. You have a choice that you can make. 이것도 어려워. It's not even difficult. I mean, one of your questions is from assignment 3. Probably ask you to do this in stack. God, either one of them. So if you practice once, it's not gonna be a problem. But I prefer my example for Q. We discussed for the supermarket cases that you have how many cashiers, and that depends on the simulation. You could do some type of simulation on the Q part, right? Those are also a problem that you can solve with the Q. Okay. So similar to a problem of section 8.3, we know what the problem is. This time, holding track lie between the input and output tracks following same conditions. Moving car from the holding track to the input track or from the output track to holding track is forbidden. Blah, blah, blah. It's the same stuff I explained. These tracks operate in FIFO manner, Q manner. Reserve track HK for moving cars from input track to output track. So the number of tracks available to hold car is K minus 1. Just playing with the numbers. Just plug the numbers and you will see what you mean. I mean, this will be good enough to give you an idea. Let me just read it. I guess this might answer your question better. What happens if no feasible holding track exists? For example, if there's not enough track to do it, then rearranging railroad problem is not a possible solution. So that's coming back to your question. That we need to have a reasonable, certain set of numbers to do it. When a car is to be moved to the holding track using the following selection method. Move a car C to a holding track that contains only car with the smaller labels. Smaller labels, 6 is about to go and 3 is smaller than 6, so I put it here. That's the rule they explain right here. If multiple such track exists, select the one with the largest label at the left and largest left end. Largest left end, the same thing. Otherwise, select an empty track if one remains. What happens if no feasible solution? That is not possible. Same figure is given in 9.11. Yeah, it's 9.11. Please read the description. It's only a paragraph. Just don't. Now, I explain briefly. Please do try to read it on yourself too. 읽어봐. 그냥 내가 설명했다 넘어가지 말고 그 아래 설명 꼭 한번 읽어봐요. They might do it differently. Especially for this section, the stack example ones. I mean, you might need to read twice because their explanation is a bit confusing. But because they hide some conditions, it's not easy to implement. But it's, twice, then you will understand how they actually did it. Okay? 뭐야? 다음 뭐야? What is the time complexity of rearrangement? Order of number of cars by tracks. Okay, for your reference, I can come back to this later. I mean, this depends on the implementation. Implementation in the book is following this order of number of cars by track. Will give you the. If you think about it this way, the big bound, I might need to put single one into k queues in worst cases, maybe every queue. That's why they times this number to this. But this is one of the implementation of the book, so it's not the only one way of looking at the problems. Okay, I'm gonna return this book. Not mine. 잊어버리려고. Thank you. It's like a quiz. It's not even an IQ test. Very easy problems. 그죠? 그냥 별로 어려운 건 아닌데. 별로 어려운 건 아닌데. 대학에서 이런 걸 가르친다는 자체가 좀 문제가 있지 않을까. 너무 쉬운 걸 가르쳐서. 문제 자체는 어렵지 않은데 이제 데이터 스트럭처를 배웠으니까 데이터 스트럭처를 이용해서 하면 프로그램도 짤 수 있다. 뭐 이런 식으로 받아들이면 될 것 같아요. 누구냐? 그 친구 안 왔네. We have one exchange. George. You know what he told me a couple of days ago? He came to my office. He looking at the curriculums in his university in Canada, and this type of course is coming on 3rd, 4th year in his curriculum. That's too late. I mean, usually 2nd year might be right. You guys taking a bit faster than the others. So, but still, you guys smart. You guys can handle this. So that's where you are at this point. So they gave you a bunch of other problems to look it over. I can tell you that these sections you might not need to read your textbook unless you really wanted to know these problems. What's in the slide probably good enough. So I'm gonna make that section that explain each problem. You don't have to read it. I mean, unless you really insist. So another application is wire routing. Let me go back to the slide that says wire routing. 여기 안 나왔구나. It's a problem for maybe we can use a Q to do it. I mean, different problem. Similar to a rat in the maze problem in section 8.56. 8.56 define the rat in the maze problem. Basically, they give you the maze. What is a maze? 미로. And they put a rat where the starting position of that maze, then rat eventually find a way out. That's the rat in the maze problem. And I think in that problem, they try to use a stack to find a way out of it. And you can take a look if you are interested. I mean, okay, so right in the major problem in 8.6, this time they has to find the shortest path between 2 points to minimize signal delay. Blah, blah, blah. In this type of board design, what does it look like? I mean, it's like a computer board or even CPU. If you enlarge in CPU, it's all the path. This is all the paths from one chip to the other. Usually their job is the designers, architect of this type of chips. Their job is to find the shortest path from one place to the other. So, and they try to make a large point. Also, another problem is like they like to avoid like crossing point, these type of stuff. They like to minimize this stuff. I'm not electrical engineer, so I don't know too much of it, but that's a basic idea. So they try to map this type of stuff on the grid, and then hopefully they can find the shortest path between these 2 points, A to B. Again, if you're interested, you can take a look on this page. I'm not gonna go into these details. But here are the algorithms to find the way between the two. If you take a look at it, it's quite simple. The basic idea is they actually write down how much it takes from my position to the next position. They just start putting the numbers in. Later, you add those numbers in, find the minimum ones of doing it. So let's take a look at the example. The shortest path between the grid. Grid is, 이거 grid라 그래. Grid. We're living in a grid. We're living in a matrix, 그죠? That's a grid. 맞나? The first step is distance labeling path, labeling the grid. You put the numbers into each spot, most likely a distance information. And then, based on those distances, you start to try to find the path that gives you the minimum of the sum and the path. Finding shortest path. 이거 어디서 하지? Did we cover Dijkstra in? Yeah, in the introduction to computer science. You can find out the similarity. What was the Dijkstra? That reminds me. It was an algorithm to find the shortest path from one location to the other. 그죠? It's to be more formal, I think, from one node to the every other node, I think. 그죠? If you remember that, we're not discussing that. What was the time complexity of those Dijkstra, if anybody remember? Huh? I mean, it also depends on the implementation. Was it n square? Order n square? Or if you do a better implementation, you can achieve n log n. It's only, what? Not even 6 months ago. It's 3-4 months ago we discussed that. 그죠? 휘발유야. 벌써 다 날아갔어. So let's take a look. Labeling the grid. So starting from position A, label is reachable neighbors. Reachable neighbors, that one is next to me, up, down, left, right. And next, the reachable neighbors of the square labeled 1 are labeled 2. So this is my starting position A. The one that I can go to is a 1 step. So I'm going to put the number here as 1, 1, 1. From this 1, the next position that you can go to, I'm going to put the number as a 2. Increase by 1 again. So in order to go to here, I have to go or likewise, from the position whose label is 2, next position, we're going to call that as a 3. I'm adding another 3. So I increase the number and representing how many moves that I have to make in order to get there. So this labeling process continues until we either reach B or have no more reachable squares. So the goal of this problem is just get to the location of the B, right? So we do this labeling stuff until we found the B or there is no space in this grid. Blah, 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 blah. Shaded squares are blocked and squares, so you cannot go to. Blah, 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 blah. By looking at this point, you can just find out how many moves that you need. A up to here is A, so probably 8 plus 9. No, 8 plus 1, 9. You might need 9 moves to do it. So that gives you a cost information. Finding shortest path. After you labeling all the nodes, and then you can do this way. Starting from position B, move to any of this neighbor labeled 1 less than B's labels. Such neighbor must exist in each grid on the one more than the other, at least of the 4. Blah, blah, blah. We have moved to one of its neighbors whose label is 1 less, so on until we reach A. So they wanted to go backward from B this time. And then they actually decrease the number by 1, and hopefully they can find the shortest one to the A. 그냥 숫자만 계속 따라가면 작은 넘버로 8, 7, 6, 5 할 수 있는 대로 계속 따라가면 that gives you the shortest path. There may be a multiple path with the same cost. That's also possible too. So 8, 7 작은 숫자만 계속 따라가는 거예요. 더 작은 숫자가 있으면 그쪽으로 가고. Okay. If you have the entire move sequence of moves, then that's the path that you have the shortest move to the position A. So you do a backward from this time from B. Okay. So 2 short algorithms are implemented in order to solve this wire routing algorithm. Is to labeling the grid by 1, and after you've done that, you will try to find the minimum ones by starting from B to decrease the number, and you will have your shortest path. I don't have to do this, do I? 이거 그냥 해. It's not even a problem. That's why I'm never gonna ask you this problem in my exams. 이거 뭐 1, 1, 2, 2, 3, 3, 4, 4, 4. Do it. I mean, or the figure 9.13 will give you the answer in the textbook. So those are very, very easy stuff to look at. 다 좋네. Sorry, I forgot. This is how the process is. Is there only one shortest path? Probably not. Can find more in other cases. Image component labeling, another problem. Let me just read it again. I'm not gonna go into in depth. Image component labeling for queuing applications. Background information. Digital images are M by M matrix of the pixels. We all know that from the course last term, Introduction to Computer Science, we mentioned of that, right? Images are the numbers. The numbers are in the format of matrices, right? In the binary image, its pixel is 0 or 1, either white or black and white, black and white. Zero pixel present the image background, while 1 present the point and the image component. So 1 is a dot, 0 is some background image. Let's say it's a white. 2 pixels are adjacent if 1 is to the left, above, right, or below the others. It's densely together. It's one position left it. That's there. 2 component pixels are adjacent the pixels of the same image components. Blah blah blah. We know how to make an image using the 0 and 1s. And the problem is labeling the component pixels. So 2 pixels gets the same label if they are the pixels of the same image component. What it says is if you see an image file, I mean it's just the colors usually in the same region, they usually have a similar colors in it. That's what they mean. So they like to they like to label those components sharing the same type of images nearby. Hey, 재미없어. I'm gonna skip this too. It's the same thing, image component labeling problem. Again, if you're interested, you can read it. Otherwise, don't worry about it too much. Just for your fun. But this is our problem to look at. Of course, I already told you I will ask this for your assignment questions. Or did I already ask you? Did I give you assignment 3 yet? 아직 안 줬어? Why? Why am I not? Maybe this week or right after the midterm. I don't care. By the way, everyone download the solution to assignment 1 and 2. Okay? 그죠? Don't send me email the night before. 일요일 밤에 메일 보내는 사람 있으면 공개할 거야. 저번에도 있었던 것 같아. Anyway, okay. This is the end of the queue. It's pretty much, by now it's pretty much straightforward. I mean, it's queue, stack, ADTs, even before array, list, linked list, chain. Now you see the pattern, and now you are a bit more familiar with it. Some people are still concerned with it. There are many new concepts in it, but it's pretty much the same thing. It's extending from the very basic class of array list or the chains to adopt this type of special restrictions on the data structures. Okay, so you shouldn't be worried too much. 하도 죽겠다고 그래가지고 I'm saying it over and over. Okay, before I forget, let's take a look at 7.1을 나갈까? 아니면 리뷰를 한번 볼까요? 리뷰를 먼저 보고 별로 리뷰할 거 없으면 7.1을 나갑시다. 별로 할 게 없더라. 내가 오기 전에 한번 봤는데. There's not much to review. Instruction space, did I discuss this too much? No. No. But notice that there's stack space. I think when we're discussing this part, I kind of skipped the stack space because we didn't cover stack. This is the space that you need to run the program. Usually function calls will be stored in that stack space. It's using it like stack. Pop it up. Okay. Data space. I mean, these things are good to know, but I would never ask you whether you memorized that or not. Okay. Data space, maze. Okay. Let's see. I'm also try to remind myself what kind of questions that I ask. Stack space, again, we kind of skip through in this part. Okay. Okay. Time complexity is amount of computer time the program runs. Okay, what do we care? But we didn't care too much about this, right? This is actually the time that we try to look at. I mean, there are later some examples of the sorting algorithm, but that is being done too fast. So you need to do it 1,000 times in order to get the average value of it, right? One of the common questions was from the textbook is one of the example was referring to an average time cost, and they actually divide it by n. And you guys wasn't sure why that was divided by n because they say so in average. So that's why they wanted to divide everything by the total number of steps they had done. Okay. Operation count, step counts, asymptotic complexity. These are the maybe key things that I may be able to ask you. More of an example like 뭐가 있을까? Worst case, best case, okay. For comparison, yeah, maybe these type of questions. I think also some of the questions from the assignment, probably I give you a very small piece of code and asking you which one is doing how many comparisons. Try to give me two. In this case, how many comparisons? The other case, how many comparisons? Give me the numbers. I'd like to see whether you understand the code that what it's doing. Again, it's not C++. I don't care about that. Just understand the context of the code. So these type of questions might be reasonable to ask. Okay? How many function operation has been called? Like these total comparison. Well, these things basically leads to a big O definitions and little O definitions, omega definitions, right? Operation counts, step counts, know what they are, program steps. You should be able to write down those numbers if I give you a small piece of code. Step count, operation count. Be careful what you're writing, frequencies and stuff. Like this. Yeah, this is a reasonable page that I can give you what this is. How many times it's being called, because it starts from 1 to n, and it will be called n-1 times inside. I might give you another one inside here, another for loop inside that is n-1 times, maybe n-1. Eventually these two are n square times. So these things, it's a reasonable task for me. Okay? 지금 설마 이게 뭐 하는 거야? 라는 사람 한 거, 나 잘못 들었지? 아니지. We did this. I did explain this. Everything. Asymptotic complexity provides a meaningful statement about the time and space complexity of a program. Why are we doing this? Just to give you an idea of certain algorithm taking what, how long. So we like to give them a reasonable boundary values to compare a set of algorithms, which one might be faster or not. And I don't know how many times I make an emphasis on, complexity examples. Like one of the questions in the assignment, I probably give you a inequality formula and ask you to get the value. What is the boundary values that this inequality function breaks or something? Right? There are similar questions. In the assignment, it was probably giving you some inequality function and asking you whether that satisfy a order of n square or not. Proof questions. 있었죠. 왜 처음 본 사람처럼 얘기해? 그죠? Those are the typical questions I might be able to ask you. Okay? Okay. These one too. I mean, what should be the condition for this one to be safe? Something. N greater than 98. I probably ask you to compute this value. 98. You should be able to give it to me. And one and only big O, omega, theta, little o. What did I ask about this stuff? I don't know how many times that I said, but memorize, memorize, memorize. Not this, but formal definition of each, right? Mathematical definition of each. Never hurt you. So know what they are in the like providing upper bound, lower bound, bounded from above and below. Little o. I don't care too much, but it's very easy to memorize it as well. I mean, just difference between those definitions is inequality signs, extra conditions, for example, for thetas. So, okay, yeah. Definition: Fn big O of Gn. Read it as Fn is big O of Gn. If and only if positive constant C and 0 exists such that Fn is less than equal to C times G of n for all n is greater than equal to n 0. Right? These are the big O definitions, big O notations, why we're using it. And this one, order of asymptotic complexity, linear, quadratic, exponential. If I give you those functions, you should be able to tell me which one is the worst one. Okay? If n goes to infinity, it's a asymptotic complexity. So you should be able to line it up and tell me. 내가 뭐 쪽집게야. 내가 낸 문제를 왜 이렇게 다 가르쳐줘야 되지? 그렇죠? 이해할 수가 없는 상황입니다. Space complex, time complexity, okay. 다 얘기해주네, 다. 미치고 환장하겠다. Okay. So in this slide, those definitions, you should take a look at it. Practice ones, common growth rates. These are the good practice to see it. 뭐 여기서 뭐 뻔하지. This slide, if I don't ask anything about the big O, big N, big O's, little O's, then it's a problem. So most of the questions will be coming from this one. And instead of programs that I give you, I'll probably ask you what would be the time complexity of certain programs. Okay, so this is probably the most important slide that you can study for. Performance, memory access patterns. I hope you can compare this order n square, which one is bigger than the others. Memory hierarchy, we briefly mentioned. In this case, you can use a CPU cycle as also performance measurement part. I mean, if it's expensive, for example, expensive memory closed CPU, it will be costly. If it goes like main memory that you guys have large ones, then it will be slower, right? It's slower, so more CPU cycles that you need to access those memory patterns. This is more of a performance measurement part, not the performance analysis part for asymptotic complexity. Blah, 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 blah. What was the reason of typically choosing 3 values of n? I think there is a small section there I want you guys to read it. Like one small one, really big one in the middle. So they can give you roughly average, like, so they can have an idea of how long it would take, right? Those are reasons were written in the textbook too. I don't know which page. They probably say it. And what was this about? What was this about? Just they want you to do some measuring certain within the part of the code, or how long it actually takes in your computers, right? What was the method they presented? I think they get the time before the function start, and then they also get the time after the function finished. So you subtract from end time to the start time, you get the value. But what was the problem of that? 뭐야? 전혀 처음 듣는 사람 같은 표정으로. 그죠? This was what I was mentioning. What was the problem of this approach? 너무 작아서 the difference is just too minimal, just too fast. So most of the values turns out to be 0 if you just do a few measurements, right? It probably takes microseconds, but those differences just too minimal. It's just displayed as a 0. So what was the solution approach they actually proposed? Yeah, do maybe 1,000 times, 10,000 times, take an average of it, and then you might have meaningful figures at the end, not 0, maybe something like 0.0012. So that was also mentioned. The code is also given in the textbook, right? It seems to be I'm the only one who remembers this from the slide. I don't need to take this course. You guys need to take this course. 그죠? Takes milliseconds. My time, it's just doing what I just described. Read chapter 4. But I would prefer to study more on the previous chapter on asymptotic complexity. If you're running out of time, do take a look at the previous slide, okay? And then if you have time later, please take a look at this. Again, order of a study for the midterms is, what was the first thing that you should do? 그래. It's slightly different from the course to other courses. Assignment, slide, and then textbook. 그죠? 몰라. If you're confident, go backward. Textbook, slide, assignment. It's not going to help you much. Okay, that was 2.1. 3.1 was, all right. I may miss some. I don't remember all the questions. I may miss some. So don't blame me if I just skip some slide. 나 욕하지 마. 나 기억이 안 나. 어느 슬라이드 나왔는지. 그러니까 내가 넘어갈 수 있으니까. 뭐 얘기 안 한 게 나왔다. 이런 얘기 하지 마. 그죠? Okay, data structure. What is ADT? Can you give me a definition of ADT? Yeah, hopefully you can. I may or may not ask you, but I don't know, maybe, but that's reasonable to ask. ADT is collection of the data and set of operations that is performed on the data, blah, blah, blah. Separation concept from implementations that we all know. Linear list. Do I ever ask you the definition of a linear list? Probably not, never. We all know what it is. It's reasonable that I can give you set up this ADT and ask to use some of it. The problem is, in the midterm, we didn't cover too much ADTs. I mean, not too many data structures yet. So more likely questions for like final exams. But 내가 지금 헷갈려. 기말고사에 물어보야 되는 건지 중간고사에 냈는지. Anyway, it's reasonable for me to ask, give you set up these functions and asking to use it to implement some other functions. Okay, just like the examples that we saw from a queue stack example, we use a previous classes like array list class and chain class to implement like functions like empty, add, stuff. So those are typical examples that I can ask you. Array-based, link-based, and direct accessing simulated pointer. Okay. 뭐 여기서부터 물어볼 게 없지. Maybe the kind of complexity of each operations in ADT. Yeah, this is constant. Understand why this is a constant operation. Find as well, search as well. The thing is, the functions that I give you in the exam may have a different definition on the slide. So be careful. Just don't assume that the function that I give you have the same type of operations in the textbook. If the operation changes, then there is a chance that time complexity may change. Okay. Delete input, output. What did I say about having these type of questions? Giving you a piece of code, asking what is time complexity. If you don't know what it means, what is the best things to do? Take the most appearing ones. Like, 안 되면 뭐 order n 아니면 order n square겠지 뭐. Just pick one. Don't forget there's a log too. Don't forget there's exponential ones too. But just pick ones that appear in the most. What is the easiest way of looking at these problems? I mean, if you really don't know what it does, you see a for loops and 2 for loops inside then n square. That gives you the chance of getting the mark. Okay, that is chapter 5, I guess. 다 했네. 아이고. Linked list, pointer, chain. As long as you know how to draw this, time complexity problem of this linked list shouldn't be a problem, right? Right. It's just basically the problem might come whether you wanted to add an element in the front or back. That gives you a different type of complexity. And what if you want to add an element in the middle? What is the time complexity of that? Right. In terms of big O. So whether it's a constant or big O of n stuff. Okay. Again, the set of ADTs, each one provide the time complexity of each operations that you have to do. So try to understand how they come up with the values down there. Pretty much same thing. Delete, order n index. Why is it order n index? Insertion and deletion. Why it says order of the index? Because I think in these operations, they tell you where to add an element. So you need to get there. That's why they say order of an index. Or order n is also fine. That doesn't really matter to me. Head node. Okay, circular. Just know some of the advantages of using a circular node, double linked list, single linked list. What does that mean to have those stuff? What if I ask a same function, but one using single linked list, the other one is using double linked list? Then I'm asking you the time complexity of doing a certain operation. Can they be equal? Right? Hopefully, the reason we're using double linked list or circular linked list, hopefully that in some cases we have a less number of comparisons of less number of moves. I mean, you see that from the Q examples, right? QRA examples too. Like these ones. Why this was they say it's a faster and slower. This is not using a circular list, linked list, just a linked list. They put it out this point. While in the condition, they compare two things. This one just compare one thing, so that's why they say it's faster. But I also said that this is not the only case of doing it. So this is just one of the examples to see if you emphasize more on the comparison. In this case, circular linked list have a less number of comparisons, so it should be faster than just single linked list. Okay. 만약 이렇게 주고 왜 이게 어느 게 더 빠르냐 물어보면 어떻게 해? 어느 게 왜 더 빠른지 하고 justify your reasons. Justify your reasons. Then you should be able to explain to me. To be honest, in the midterms, I'm not going to ask you too much of programming. Like in the finals, I may ask you a few questions on programming. Like, but in here, more focuses on programming analysis. And which one is faster? Whether you know how to read a set of code. Okay, the things that we have emphasis on. This one is array and matrix. Matrix. When I hear the word matrix section, row major column ordering, row major ordering, column major ordering. What was the reason of using those techniques in matrix operations? Yeah, we like to reduce the space complexity. Maybe we need two-dimensional arrays to store all the values, but it might be a way to store everything in 1D array, so less space to use it. That's why we also take a look at a special type of matrices, right? How many was there? Diagonal, tridiagonal, and upper tridiagonal, lower tridiagonal, sparse matrix, dense matrices. I mean, all of those are there to demonstrate the point that we can use a smaller space to store all the matrix in it. We don't need every space there. So you should know how to present that in the 1D matrix or other formats. Okay, those conversion steps that you should know. But this will be very, very easy questions on this part. 여기 나오네. Diagonal, tridiagonal, symmetric, sparse. We will mention a transpose. Memory problem, memory, space, space. Low major column ordering, column major ordering. It's like kindergarten stuff. You can see. Mapping functions, you might need to just practice once. Okay. It's pretty much obvious. I mean, it's the exact same step. You do a matrix into a row major column ordering into 1D array, then there is a simple function to use, right? I times n plus 1, something. It's not so much different from that very basic function calls from those two ordering method. 다 했다. Done. So yeah, the midterm will be covering up to matrix part, okay? 에이, 물어볼 게 없다. Okay, done. I think I explained.